The Earth is a rocky planet that rotates in a near-circular orbit around the Sun. It rotates on its axis, which is a line through the North and South poles. The axis is tilted at an angle of approximately 23.5 degrees from the vertical. The Earth completes one full rotation revolution in approximately 24 hours one day. This rotation creates the apparent daily motion of the Sun rising and setting. Rotation of the Earth on its axis is therefore responsible for the periodic cycle of day and night. Day and night. The Earth's rotation around its axis creates day and night. Day is experienced by the half of the Earth's surface that is facing the Sun. Night is the other half of the Earth's surface, facing away from the Sun. Use this image. Day and night are caused by the Earth's rotation. Rising and setting of the Sun. The Earth's rotation on its axis makes the Sun looks like it moves from east to west. At the equinoxes, the Sun rises exactly in the east and sets exactly in the west. Equinox, meaning equal night, is when day and night are approximately of equal length. However, the exact locations of where the Sun rises and sets changes throughout the seasons. In the northern hemisphere, above the equator. In summer, the Sun rises north of east and sets north of west. In winter, the Sun rises south of east and sets south of west. Use this image. The Sun rises in the east and sets in the west. Its approximate area changes throughout the year. The Sun is highest above the horizon at noon, 12 p.m. In the northern hemisphere, the daylight hours are longest up until roughly the 21st of June. This day is known as the summer solstice and is where the Sun is at its highest point in the sky all year. The daylight hours then decrease to their lowest around the 21st of December. This is known the winter solstice and is where the Sun is at its lowest point in the sky all year. The Earth's orbit. The Earth orbits the Sun once in approximately 365 days. This is 1 year. The combination of the orbiting of the Earth around the Sun and the Earth's tilt creates the seasons. Use this image. Seasons in the northern hemisphere caused by the tilt of the Earth. Over parts B, C and D of the orbit, the northern hemisphere is tilted towards the Sun. This means daylight hours are more than hours of darkness. This is spring and summer. The southern hemisphere is tilted away from the Sun. This means there are shorter days than night. This is autumn and winter. Over parts F, G and H of the orbit, the northern hemisphere is tilted away from the Sun. The situations in both the northern and southern hemisphere are reversed. It is autumn and winter in the northern hemisphere, but at the same time it is spring and summer in the southern hemisphere. At C, this is the summer solstice. The northern hemisphere has the longest day, whilst the southern hemisphere has its shortest day. At G, this is the winter solstice. The northern hemisphere has its shortest day, whilst the southern hemisphere has its longest day. At A and D, night and day are equal in both hemispheres. These are the equinoxes. Did this video help you? Yes. No. Moon and Earth. The Moon is a satellite around the Earth. It travels around the Earth in roughly a circular orbit once a month. This takes 27 to 28 days. The Moon revolves around its own axis in a month, so always has the same side facing the Earth. We never see the hemisphere that is always facing away from Earth, although astronauts have orbited the Moon and satellite have photographed it. The Moon shines with reflected light from the Sun, it does not produce its own light. Phases of the Moon. The way the Moon's appearance changes across a month, as seen from Earth, is called its periodic cycle of phases. Use this image. Phases of the Moon as it orbits around Earth. In the image above, the inner circle shows that exactly half of the Moon is illuminated by the Sun at all times. The outer circle shows how the Moon looks like from the Earth at its various positions. In the new Moon phase, the Moon is between the Earth and the Sun. Therefore, the sunlight is only on the opposite face of the Moon to the Earth. This means the Moon is unlit as seen from Earth, so it is not visible. At the full Moon phase, the Earth is between the Moon and the Sun. The side of the Moon that is facing the Earth is completely lit by the sunlight. This means the Moon is fully lit as seen from Earth. In between, a crescent can be seen where the Moon is partially illuminated from sunlight. The solar system. The solar system consists of the Sun, 8 planets, natural and artificial satellites, dwarf planets, asteroids and comets. The solar system. The solar system consists of one star, the Sun, and the objects that orbit it, including the planets, moons, dwarf planets, asteroids and comets. The planets. There are 8 planets which orbit the Sun. In ascending order of the distance from the Sun, these are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. The planets can be divided into 2 groups. The inner rocky planets. The outer gas giants. Dwarf planets. A dwarf planet is an object similar to a planet, but much smaller. The gravitational field around a planet is strong enough to pull in nearby objects with the exception of natural satellites. Whereas, the gravitational field around a dwarf planet is not strong enough to pull in nearby objects. Satellites. There are two types of satellites, natural and artificial. Natural and artificial satellites of Earth. The Moon is a natural satellite of the Earth. Many artificial satellites orbit around the Earth. Natural satellites are objects that orbit planets. A moon is a type of natural satellite. Artificial satellites are man-made objects that orbit another object in space. The International Space Station, ISS, is an example of an artificial satellite that orbits the Earth. Asteroids and comets. Asteroids and comets also orbit the Sun. Locations of asteroids and comets. Asteroids are found in the asteroid belt between Mars and Jupiter, whereas comets are usually found in the outer reaches of the solar system due to their highly elliptical orbits. An asteroid is a small rocky object which orbits the Sun. The asteroid belt lies between Mars and Jupiter. An asteroid. Asteroids are small, rocky objects which occupy the inner solar system. A comet is an object made of dust and ice which orbits the Sun in a highly elliptical path. The ice melts when the comet approaches the Sun and forms the comet's tail. A comet. Comets are small, icy objects which occupy the outer solar system. Orbiting bodies. The solar system is made up of many bodies which orbit around other bodies. Smaller bodies orbit around larger bodies. For example, planets orbit the Sun and moons orbit planets. The orbiting bodies in the solar system are shown in the table below. Table of orbiting bodies in the solar system. Orbiting body. Body it orbits. Planet. The Sun. Moon. Planet. Comet. The Sun. Asteroid. The Sun. Artificial satellites. The Earth. Exam tip. You need to know the order of the 8 planets in the solar system. The following mnemonic gives the first letter of each of the planets to help you recall them. My very excellent mother just served us noodles. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Analyzing orbits. Extended tier only. Over many years, data for the planets, moons and the Sun have been collected. Some of this data is shown in the table below. Data for the planets in the solar system. Planet. Mean distance from Sun relative to Earth. Orbital period, Earth years. Mean surface temperature, degree C. Density, kilogram, m3. Diameter, 103 kilometers. Mass relative to Earth. Surface gravity, n per kilogram. Number of moons. Mercury. 0.39. 0.24. 350. 5,429. 4.9. 0.06. 3.7. 0. Venus. 0.72. 0.60. 460. 5,243. 12.1. 0.82. 8.9. 0. Earth. 1. 1. 20. 5,514. 12.8. 1. 9.8. 1. Mars. 1.5. 2. Minus 23. 3,934. 6.8. 0.11. 3.7. 2. Jupiter. 5.2. 12. Minus 120. 1,326. 143. 320. 23.1. 63. Saturn. 9.6. 30. Minus 180. 687. 121. 95. 9.0. 61. Uranus. 19. 84. Minus 210. 1,270. 51. 15. 8.7. 27. Neptune. 30. 160. Minus 220. 1,638. 50. 17. 11.0. 13. The data allows us to make comparisons, identify trends and anomalies, make predictions. Some examples of comparisons are: Neptune is 30 times further away from the Sun than the Earth. Jupiter contains the same mass as 320 Earths. An example of a trend is: as the distance from the Sun increases, the time it takes to complete one orbital period also increases. An example of an anomaly is: as the distance from the Sun increases, the temperature decreases, except for Venus, which has a higher temperature than Mercury. An example of a prediction is: the temperature of a dwarf planet in the asteroid belt is likely to be around minus 100 degrees Celsius, but it could be anywhere between minus 63 degrees Celsius and minus 130 degrees Celsius, as these are the temperatures of Mars and Jupiter. Exam tip. Don't panic when you see the large table of numbers, you don't need to memorize any of it, but you need to be able to analyze and interpret it confidently. Look for trends such as one variable increasing whilst the other decreases or increases. Think carefully about why that may be with what you have already learned about the planets from this topic. For example, what is the planet made of? What is its distance from the Sun and how does this affect it? Formation of the solar system. The 4 inner planets nearest to the Sun are rocky and small, have atmospheres, except for Mercury. The 4 outer planets furthest from the Sun are gaseous and large, are mostly composed of hydrogen and helium gas. The planets in the solar system. The 8 planets can be split into the 4 inner rocky planets and the 4 outer gas giants. The differences between the inner and outer planets can be explained using the accretion model for the formation of the solar system. Distribution of elements in the solar system. The Sun and the planets in the solar system formed from a cloud of dust and gas nebula. Gravity pulled this cloud together into a giant ball, which would eventually become the Sun. As the nebula collapsed, the Sun became denser and hotter. The solar system then formed around 4.5 billion years ago. The planets formed from the remnants of the matter left over from the nebula that formed the Sun. The nebula contained many elements that were created during a supernova explosion in the distant past. As the early Sun became hotter, gaseous matter was pushed further out into the solar system than solid matter. A nebula. A nebula is an interstellar cloud of gas and dust. Formation of the inner planets. In the hotter regions, closer to the Sun, the temperature was too high for lighter elements to exist in a solid state. Therefore, the inner planets formed from materials with high melting temperatures such as metals, e.g. iron. The original nebula contained only a small proportion of heavy elements, so the inner planets could not grow as significantly as the outer planets. As a result, solids in the inner disk were pulled together by gravity to form solid planets. This is why the 4 planets nearest to the Sun, Mercury, Venus, Earth and Mars, are rocky and small. Formation of the outer planets. In the cooler regions, further from the Sun, the temperature was low enough for the light molecules to exist in a solid state. Therefore, the outer planets formed from materials with low melting temperatures, e.g. hydrogen, helium, water and methane. The original nebula contained a large proportion of light elements, so the outer planets were able to become exceptionally large. As a result, gases in the outer disk were pulled together by gravity to form gaseous planets. This is why the 4 planets furthest from the Sun, Jupiter, Saturn, Uranus and Neptune, are gaseous and large. Formation of the accretion disk. In the nebula, matter accreted. This means attractive gravitational forces between particles caused them to join together and grow into larger objects. As the cloud collapsed under gravitational forces, it began to spin faster. It became hotter. It formed an accretion disk. From the rotating accretion disk, the Sun and the planets emerged. The Sun formed at the center. The planets formed in the accretion disk. Formation of the solar system. The solar system formed from a nebula with the Sun in the center, then solid planets closer to the Sun and gaseous planets further away. Exam tip. When writing about the formation of the solar system, make sure you can state where solid and gaseous matter gathered in the solar system. Explain how heavier elements became a part of the nebula. Describe the role of gravity in pulling matter together and the formation of an accretion disk. Explain the difference between the planets in terms of the accretion model. Light speed calculations. Light is a type of electromagnetic wave which travels at a constant speed of 3 times 108 meters per second. Objects in the solar system are visible from Earth as they reflect light from the Sun. It takes time for light to travel such large distances, for example. It takes 8 minutes for light from the Sun to reach Earth. It takes around 5 hours for light from the Sun to reach the outer regions of the solar system. It takes 4 years for light from our nearest star, after the Sun, to reach Earth. The Milky Way galaxy contains billions of stars, huge distances away, with the light taking even longer to be seen from Earth. To carry out light speed calculations, we can rearrange the equation. So, the time taken for light to travel a distance can be calculated using worked example. The radius of Mercury's orbit around the Sun is 5.8 times 10^10 m. The speed of light is 3.0 times 108 meters per second. Calculate the time taken for light from the Sun to reach Mercury. Answer. Step 1. List the known quantities. Distance traveled equals 5.8 times 10^10 m. Speed of light equals 3.0 times 108 meters per second. Step 2. State the equation for the time taken for light to travel a distance. Step 3. Substitute the values into the equation. It takes about 193 s, or 3 minutes, for light from the sun to reach Mercury. Exam tip. The speed of light is very fast. This is why in our everyday life things like switching on a light seem to be instant. However, this is only because the light travels very fast and the distances are very small. In large, astronomical distances, which can be millions or even billions of kilometers, the limit of the speed of light starts to have an effect. For example, it takes light 8 minutes to travel from the sun to the Earth. This means we are seeing the sun as it was 8 minutes ago. If the sun was to disappear, we would not notice till 8 minutes later. Although, by that time delay would be the least of our worries. P.S. The sun is not going to vanish. Gravitational field strength of a planet. The strength of a gravitational field around a planet depends on the mass of the planet, the distance from the planet, gravitational field strength and mass. The relationship between gravitational field strength and mass is: the greater the mass of a planet, the greater the strength of the gravitational field at its surface. The value of gravitational field strength varies from planet to planet depending on their mass and radius. Gravitational field strength of bodies in the solar system. The strength of the gravitational field at the surface of a planet depends on its mass and radius. Gravitational field strength and distance. The relationship between gravitational field strength and distance is: as the distance from a planet increases, the strength of the gravitational field decreases. At the surface of a planet, the value of gravitational field strength is constant, but it decreases with distance from the planet. Exam tip. You do not need to remember the value of G on different planets for your exam, and the value of G for Earth is given on the front page of the exam paper. Gravitational attraction of the Sun. Orbital motion is a result of the gravitational force of attraction acting between two bodies. This gravitational force always acts towards the center of the larger body, causes the orbiting body to move in a circular path. The Sun contains most of the mass, greater than 99%, of the solar system. Therefore, for objects orbiting around the Sun, the Sun's gravitational attraction keeps them in orbit. The force is directed from the orbiting object to the center of the Sun. Orbital motion of the Earth around the Sun. The Sun's gravitational force of attraction keeps the Earth in orbit around the Sun. Orbital motion of planets. Extended tier only. As the distance from the Sun increases, the Sun's gravitational field strength decreases. The orbital speed of a planet decreases. For an object to maintain a circular orbit, it must have a centripetal force. For planets orbiting the Sun, this force is the Sun's gravitational attraction. Therefore, the centripetal force on a planet depends on the strength of the Sun's gravitational field, the distance of the planet from the Sun. The further away a planet is from the Sun, the weaker the strength of the Sun's gravitational attraction and the weaker the centripetal force. The centripetal force on a planet is proportional to its orbital speed. Therefore, the further a planet is from the Sun, the smaller its orbital speed, the longer its orbital period. Orbital speed and distance. The closest planets to the Sun have the fastest orbital speeds, and the furthest have the slowest. This trend in orbital speed and distance can be seen in the data of the planets in the solar system. Orbital radius, speed and period data. Planet. Orbital radius million km. Orbital speed kilometer per second. Orbital period days or years. Mercury. 57.9. 47.9. 88 days. Venus. 108.2. 35.0. 225 days. Earth. 149.6. 29.8. 365 days. Mars. 227.9. 24.1. 687 days. Jupiter. 778.6. 13.1. 11.9 years. Saturn. 1433.5. 9.7. 29.5 years. Uranus. 2872.5. 6.8. 75 years. Neptune. 4495.1. 5.4. 165 years. Exam tip. Be careful with your wording in this topic when talking about gravity. It is important to refer to the force of gravity as gravitational attraction, strength of the Sun's gravitational field, or the force due to gravity. Avoid terms such as the Sun's gravity, or even more vague, the force from the Sun. Orbital speed equation. Extended tier only. When planets orbit around the Sun, or a moon moves around a planet, they move in circular orbits. In one complete orbit, a planet travels a distance equal to the circumference of a circle. This is equal to, where is the radius of the circular path? The relationship between speed, distance and time is. The average orbital speed of an object can be defined by the equation where v equals orbital speed in meters per second, meter per second. R equals average radius of the orbit in meters, m. T equals orbital period in seconds, s. This orbital period, or time period, is defined as the time taken for an object to complete one orbit. The orbital radius r is always taken from the center of the object being orbited to the object orbiting. Orbital speed of a planet. Orbital radius and orbital speed of a planet moving around a sun. Worked example. The Hubble Space Telescope moves in a circular orbit. Its height above the Earth's surface is 560 kilometers and the radius of the Earth is 6,400 kilometers. It completes one orbit in 96 minutes. Calculate its orbital speed in meter per second. Answer. Step 1. List the known quantities. Radius of the Earth, r equals 6,400 kilometers. Height of the telescope above the Earth's surface, h equals 560 kilometers. Time period, t equals 96 minutes. Step 2. Write the relevant equation. Step 3. Calculate the orbital radius, r. The orbital radius is the distance from the center of the Earth to the telescope. Step 4. Convert any units. The time period needs to be in seconds. The radius needs to be in meters. Step 5. Substitute values into the orbital speed equation. Exam tip. Remember to check that the orbital radius r given is the distance from the center of the Sun if a planet is orbiting a sun, or the planet if a moon is orbiting a planet, and not just from the surface. If the distance is a height above the surface, you must add the radius of the body to get the height above the center of mass of the body. This is because orbits are caused by the mass, which can be assumed to act at the center, rather than the surface. Don't forget to check your units and convert any if required. Elliptical orbits. Extended tier only. The orbits of planets, minor planets and comets are elliptical. An ellipse is a squashed circle. Planets and minor planets have slightly elliptical orbits. Their orbits are approximately circular, so the Sun is generally considered to be at the center. Comets have highly elliptical orbits. The Sun is not at the center of the orbit, it is at one of the two foci of the ellipse. Elliptical orbit of a planet. Planets, minor planets and comets travel in elliptical orbits where the Sun is not at the center. Exam tip. You will not be asked to do any calculations with elliptical orbits. If you are asked to calculate the time period, orbital speed or radius of an orbit, it can be assumed that it is circular. Comet speed. Extended tier only. An object in an elliptical orbit around the Sun travels at a different speed depending on its distance from the Sun. Although these orbits are not circular, they are still stable. For a stable orbit, the radius must change if the comet's orbital speed changes. As the comet approaches the Sun, the radius of the orbit decreases. The orbital speed increases due to the Sun's strong gravitational pull. As the comet travels further away from the Sun, the radius of the orbit increases. The orbital speed decreases due to a weaker gravitational pull from the Sun. Speed of a comet in an elliptical orbit. Comets travel in highly elliptical orbits, speeding up as they approach the Sun. Conservation of energy in elliptical orbits. When an object moves in an elliptical orbit, energy must be conserved. Throughout the orbit, gravitational potential energy is transferred to kinetic energy, and vice versa. When a comet travels closer to the Sun, it has greater kinetic energy. When a comet travels further from the Sun, it has greater gravitational potential energy. As the comet approaches the Sun, it loses gravitational potential energy and gains kinetic energy. The increase in kinetic energy causes it to speed up. As the comet moves away from the Sun, it gains gravitational potential energy and loses kinetic energy. The decrease in kinetic energy causes it to slow down. Exam tip. Remember that an object's kinetic energy is defined by, where m is the mass of the object and v is its speed. Therefore, if the speed of an object increases, so does its kinetic energy. Its gravitational potential energy therefore must decrease for energy to be conserved.